From multi-story building skeletons and industrial roof trusses to transmission towers, the scale of our infrastructure is immense. Despite their different geometries, they all rely on the same core discipline, structural steel engineering. To understand how these systems work, we have to look at the micromechanics. We start with a single beam and the physics of a massive, concentrated point load. This is the central engineering challenge, taking an unpredictable environmental load and containing it within the resisting force of a manufactured steel section. The methods we use to define those limits have changed. We are currently seeing a transition from the legacy working stress design method to the limit state design framework mandated by IS 800-2007. This shift provides the mathematical framework that dictates how we define the safety and reliability of modern infrastructure. Structural steel is an engineered alloy. It begins as a molten matrix of iron, known as ferrite, and carbon, known as cementite. As the carbon percentage increases, the ultimate tensile strength follows, making the steel harder. However, there is a critical trade-off. As carbon content goes up, both ductility and weldability drop significantly. Ductility represents the material's capacity to undergo large plastic deformations without a sudden fracture. Most structural work relies on mild steel, such as IS 2062 grade Fe 410. This provides a standard baseline elastic modulus of 2 × 10⁵ newtons per square millimeter. This grade establishes a typical yield strength boundary of 250 megapascals, the standard starting point for our structural calculations. Ductility is our primary safety mechanism. It allows steel to yield locally, prevents sudden catastrophic brittle failure, shows visible evidence through heavy sagging, and redistributes stress across the structure. This is the idealized stress-strain curve for mild steel, the foundational tool for all structural modeling. This initial slope is the linear elastic zone. Here, deformation is temporary. Remove the load, and it returns to shape. Working stress design philosophy treats this exact point, the initial yield, as the definition of failure. We divide that yield stress by a factor of safety, creating a permissible working stress well below the yielding point. The flaw here is that we ignore the massive amount of strength the material still possesses after it passes the elastic limit. Beyond that point lies the plastic yield plateau. Here, the steel deforms significantly without failing. The competing plastic design method utilizes this reserve, calculating the ultimate load required to cause an actual structural collapse. While plastic design accounts for the reality of extreme loads, it applies zero safety factor to the material properties. It assumes the steel's metallurgy is always perfect. Relying on a single safety margin, whether the conservative elastic boundary of working stress or the aggressive ultimate boundary of plastic design, fails to account for independent real-world variables. In reality, material strength and environmental loads are statistical probabilities. This graph compares potential load intensities against actual material resistance. The overlap between these two curves is the probability of failure, where a high load event meets a material flaw. Limit state design is the modern framework built to isolate and minimize that specific probability. We define a limit state as any physical condition that renders a structure entirely unfit for its intended use. The first classification is ultimate limit states. These deal with life safety and structural integrity, including yielding, buckling, and fatigue. The second classification is serviceability limit states. These focus on usability and comfort, governing things like deflection, vibration, and corrosion. This shift to the limit state framework moves engineering away from arbitrary guesswork and towards a mathematically calculated target reliability. To manage this, IS 800-2007 separates external forces from internal resistance with 2 core equations. On the load side, we use partial safety factors, or gamma F, which act as amplifying multipliers on predicted working loads. The factor increases as the load becomes less predictable. A stable dead load gets a lower factor, while highly variable wind or earthquake loads receive higher ones. On the strength side, we apply gamma M. These are reduction dividers applied to the characteristic yield strength of the steel. For material resistance governed by standard yielding, we use a baseline gamma M0 factor of 1.10. Compare that to connection resistance, like bolts or shop welds. These require a higher factor of 1.25 to account for potential fabrication errors. By splitting these safety margins into partial factors, engineers can assign specific mathematical risk values to precise uncertainties. We can see the physical impact of these philosophies by designing the same structural element using all three methods. The working stress design outcome is unnecessarily massive. It is uneconomical because it adheres rigidly to the elastic boundary. The plastic design outcome is much lighter, but it is highly vulnerable to any unexpected metallurgical flaws in the steel. The limit state design outcome provides the optimal balance, an economic geometry combined with rigorous statistical safety. This optimized balance is why IS 800-2007 legally mandates limit state design for modern Indian steel structures. With this conceptual framework established, we can now apply these partial safety factors to the most critical part of any structure, the riveted, bolted, and welded connections. Structural engineering now operates as the mathematical management of reality's inherent uncertainty.